Okay, so speed time graphs. So we're going to first of all go through and just describe the motion in each section of the graph. And obviously the tricky thing here is it looks exactly the same to look at as a distance time graph. The only difference is the label on the y-axis, so we have to be really careful to check in with our graph and ask it what sort of graph it is before we start doing calculations. Interrogate your graph. What graph are you before you start asking questions of it. What's happening in this first section here where there's a horizontal line?
It's at rest.
At rest. So when it's a horizontal line, it's constant speed of 0 when that horizontal line is down the bottom. What about in this second section here where that line's sloping upwards? What's happening there?
Accelerating.
The speed's gone from 0 up to 10, and so it must be acceleration. And on a speed time graph, it's really easy to calculate acceleration, because acceleration is change in speed over change in time, change in speed, change in time. It's just the gradient again. Same as speed on a distance time graph, acceleration on a speed time graph is the gradient. So acceleration is change in speed over change in time. Acceleration is, it's gone from 0 to 10 over 20 up to 40, 20 seconds. Acceleration of 0.5 ms minus 2. What about this third section here? What's happening there? How much?
10 meters per second.
Nice, so we can just read it off. Constant speed, 10 meters per second. And the last section where it slopes back down to 0, what's happening there? Deceleration. Nice. Is change in speed over change in time. So it's gone down by 10 over a time of 40, so negative 10. Acceleration is 0.25 ms minus 2. That's the easy bit of speed time graphs. We haven't done the hard bit, which is using this to calculate distance. So we're going to come back, we're going to draw this exact same graph next time, and we're going to learn how to calculate distance from a speed time graph. So we can't just read that off, we have to be cunning about how we do it. But for today, it's enough to know that going up means acceleration, horizontal means constant speed, going down is deceleration, and we can calculate acceleration, deceleration by finding the gradient. Okay, so last time we looked at calculating the acceleration off a speed time graph and just like what it means. This time we're just going to take that to the next step and look at how we can calculate something that's not obvious at all, like the distance off a speed time graph. And the rule's really easy. The rule is that the distance travelled is equal to the area under the speed time graph. So we're going to do this the easy way, then I'm going to show you the tricky trick to do it the harder way that's much quicker. So the easy way is to break our graph into shapes that we can do really easily. We're trying to calculate the area under the graph. So our rule is that distance equals area between graph line and axis. So we've broken it into 3 easy shapes because everyone can do area of triangle and rectangle and triangle, right? So area of triangle, how do we do area of triangle?
1/2 times base times height.
Half times base times height. So we know that area is half of base times height, which is half of, how much is the base of that triangle?
20.
20. How much is the height of that triangle? 10. Half of 20 is 10, and 10 tens are 100. So the area of that triangle is 100 metres. Weird area, right? But think about it. We've got seconds as the unit for the base, and the unit for the height is meters per second. If we multiply meters per second by seconds, we just end up with meters. And so when we're using the area idea, it's legit that we end up with a distance in meters. Because we're not doing, it's not a normal triangle, it's not a meters triangle, it's a seconds, meters per second triangle. Rectangles, how do we do them? Base times height, cool, easy, right? And so for this one we've got 40 times 10. So 400 metres. And then finally we're back to another triangle, so we know that it's going to be half of base times height. So half of 40 times 10. So half of 40, 20. 20 times 10, 200, right? So how far has been travelled in that journey on that graph?
700 metres.
Cool. So total. Who's already like aching to tell us what the shortcut is? What can we do? How can we do that really easily? Well,
Area of a trapezium.
area of trapezium. How do we do a trapezium? What's a trapezium?
It's like a parallelogram but with like different, I don't know.
It's one of those shapes that have kind of like two lines that are kind of parallel and then two bits that aren't like that. Trapezium. Yeah. Which is the shape that you can see. What's the rule for area of trapezium?
I've forgotten that.
Who knows the rule for area of trapezium?
Is it? Is there a half?
Yeah, is it half?
Oh. And then is
Give
it
you a clue, we've got
the top line plus the bottom line?
We've got the top line A and the bottom line B.
Yeah.
So half of A plus B times H. So we're like averaging the A and the B, multiplying it by the height. So how much is A and B on our one?
40 and 100.
40 and 100. What's 40 plus 100? 140, half of that.
70.
So we got half of 140 is 70. 70 times 10. 700 metres. So if maths is your strong point and you know like area of trapezium and that's not stressful to remember, you can bust some mathematical moves and get that like done really, really quickly and easily. See how that's happened? Cool.